Yeah. So, welcome everyone to the second week of the TA session to the Intro to Mobile Robotics course. I am your TA Suraj Borate from IIT Gandhinagar. Uh, where someone has joined. Yes. So today's topic is basically forward kinematics, and forward kinematics means that we know the joint angles or the angles or the, if for prismatic joint we will say, maybe we will not say the angle, but we know the joint variables values, and from the joint variable values we want to know that where our end effector will lie. Okay, so that is the goal of this section. And before that, let's review some things like what are the types of robots, because such questions have been observed in your assignment. So the purpose of the TA session is like you should be able to do your assignments, and that is the prime purpose. And apart from that, to solve your doubts and also to learn some concepts, so that it's a very fluid thing. If you have something to ask or something to learn, you can always ask, and we will try to help you with that. uh, okay, so let's talk about what are the different type of robots that may arise you know in the questions. There are in the questions that are being asked. So there are a lot of standard robots. So you might have heard about you know uh, what we say, the planar RR manipulator. Okay, so when we say RR, it means that there are two revolute joints. Okay. Okay, so this is how we denote the planar RR manipulator. Okay, it is very important to say planar because, as you can think that there can be a RR manipulator which can be like this, where the links rotate in the perpendicular plane, right? So this is also RR, but this is not a planar RR. Okay, so this is one thing. Then there is something called a spherical manipulator, right? So in spherical manipulator you will have a spherical joint, and then you will have a prismatic joint, right? So this will give us 2 degrees of freedom, and then this will have one prismatic degree of freedom. Then you can have something called as a cylindrical manipulator. Okay, so cylindrical manipulator can be something like this. uh, so cubes are the indication of you know prismatic joint, whereas cylinders I am drawing as revolute joint. So you, when you see a cylinder, how it can rotate and it can slide. So that kind of motion we call a cylindrical motion. So you can see there is a cylindrical manipulator where there is first a revolute joint, and then there is a prismatic joint along the axis of the cylinder. And then if it is a two-link cylindrical manipulator, then we can stop here. But if it's three-link, then we can have one more P. So this is RPP. So the important thing is these are all names, right? But you need to understand how the links are connected to each other. Okay, so for example, SCARA. Okay, the SCARA full form is, what is SCARA's full form? Anyone? So this is something like selective compliance and articulated, something like that. So I don't recall the full form, but yeah. So these are the names, but you of robots which are commonly used in industry and or the common configurations. So when the name comes up in the quiz or in the exam, then you are expected to know what is the how it looks. Okay, so that is something you should always look up to. So for example, in SCARA, it is like okay, so my drawing is terrible. So here you can see there is one link that can rotate about this axis, and then there is one more joint. So there is one more link. So this is a planar manipulator, just like 2R if I see from the top, right? And then there is a you know a prismatic joint. So it is also RRP. So it is an RRP kind of thing, and such manipulators are very much used in industry for pick and place tasks, and these are very fast. Okay, but the drawback of SCARA is that it cannot have a lot of payload capacity, so it cannot pick a lot of weight or something like that. Right. So so what it happens is, so I can just show you some video of SCARA robot. Okay, so SCARA. So you can see here, this is the first axis and then this is the second axis. Okay, and then it is rotating. So I can show you some pick and place kind of task that it is doing at a very high speed or something like that. Yeah, so here you can see.
This is a SCARA robot I've been designing for a few months.
So this is the first
In this
axis, this is
video,
the
I'll
second
test its
axis,
precision,
and then
load
there is
capacity,
the
reliability,
prismatic
and do a
joint
few
over
other
here.
demonstrations. Along the way,
Okay. So you can so in this particular case they have put a gripper also at the end effector. Okay. So what I suggest is to whatever uh, names of robots that come up, you just look at their videos and get the intuition about how they are moving and all. Okay, so let's go on to the, so if something comes up in the question, then we will look at the image of it. Okay, so as we had said that in forward kinematics we know the joint variables, and we have to find the end effector position. End effector position. Now question arises, why? Okay, why we want to do this? Can anyone answer? What is the use of forward kinematics? So there is also something called as inverse kinematics. In inverse kinematics, the idea is that we know the end effector position and we find the joint variables. Okay, so can anyone tell me why do we, what is the application of forward kinematics? Hello, am I audible? So what that if you know the joint variables, find the end effector. So inverse kinematics is more clear, right? So usually we have a task, right, and we know that okay, my paint brush should move from here to here. Okay, so I know the end effector position where the wrist is holding the paint brush, the robot's wrist. So I know the end effector's position, that it should move like this. So I know these coordinates of all these points, right? And so in order to control the robot, I need to find the joint angles, whatever number of angles your robot have, joints you have. So I need to find the joint angles. So from here, this is what our task gives us. the end effector position, right? Task will give us end effector position, and from the end effector position we want to find the angle, so we will use inverse kinematics. So that is clear. But then why do we need forward kinematics? Okay, so forward kinematics usually we need to know because suppose we are visualizing a robot. Okay, visualization is one reason. Okay, so suppose if I want to do the animation, right? Okay, you found theta, right? In order to animate that robot, I need to draw the links, right? And in order to draw the links, I need to find for each link, let's say for each link I need to find this point. Okay, and eventually I need to find the end effector. Okay, so if I know the angles, okay, I need to find how to draw these links, and that essentially is forward kinematics. Okay, but just we are saying that the last link's end effector, but we can use forward kinematics because if we cut the robotic arm over here, this is also like a kind of subset, right? So we find all these points and we animate. And if time permits, we will try to do that in MATLAB today, or we can do it next time. So that is not the primary goal currently. Okay, so visualization. The second thing is we can do some kind of predictions. Okay, uh, I have to add the people who are continuing to join. I am sure there might be some kind of setting that will allow everyone to join directly, but let's do that from next time. Okay. Okay. Second thing is that we need to sometime predict what will happen if we give certain joint angles and all, and try to understand what is the in design aspect, like when we design a manipulator on, we want to know that okay, if I keep certain link lengths and certain joint angles, okay, what is my workspace going to look like, what is the size of my workspace and all, and in that case we need to plot the workspace and see how it looks, and for that uh, we need forward kinematics. Okay, so now let's go on to the ds parameters. Okay, so what is ds parameter? Okay, so for that I have a simple question that to ask to you is that if I have two frames, okay, these are free floating frames, how many to define the relative pose between the frame. When we say pose means position plus orientation, both. So what is the relative orientation and relative position between the frames? How many parameters do I need? Anyone?
Four parameters.
No. So these are free
Six.
floating frames, right? So these are not constrained in any way. So this is frame A and this is frame B. I have just given them arbitrarily. How do I compute the homogeneous transform between these two frames, right? So there are three orientations, right? With respect to this, it has been rotated by three angles, right? We have seen roll pitch or some other representation, and three position x, y, z, right? So there are six degrees of freedom, or six. Let's say we need six parameters to find the transformation between these two frames. But what happens if we say that one of the frames, okay, so these 2 points are rigidly attached, okay, so there is a link between these 2 points, and then one of the point is a joint. As soon as we say that one of the point is a joint, we define something about that joint, Okay, so that joint will be defined somewhere, has to be somewhere, and we do define something about it. What do we define about it? So we give it a nature, like we say it is a revolute joint or a prismatic joint. Okay, and when we do this, what happens is we restrict the number of degrees of freedom of this point A. Okay, and depending on how many degrees of freedom are restricted, the these six parameters can be reduced. Okay, so as you know, for a revolute joint, okay, what happens to a revolute joint when we put a pin on like something here? You know what happens is now the revolute joint uh, cannot move out of this plane, right? So there are some constraint into this. So if you see a revolute joint will impose, let's say in a planar case, so that is more easy to visualize. So earlier, if this was not pinned over here, this link would have moved in x, y, and theta, right? So it would have three coordinates to define it completely. But because we have pinned, now only theta is enough to define any position of the link, all possible position. So a revolute joint reduces 2 degrees of freedom. Okay, so that is why it is 6 minus 2, 4. So this kind of intuition, because why there are 4 DS parameters and only 4 things are required to you know do the transformation between the two frames, uh, even though there are 6 degrees of freedom, right? So that is the intuition. You can ponder about it later. I have not given a very rigorous this thing. It's just an intuition. You can refer to any book and you will find over there. Okay, so once we understand this, that there are 4 DS parameters. Now the thing is, if there was a spherical joint or some other kind of joint, okay, which has more than like which restricts more than 2 degrees of freedom or something like that. Okay, then what happens is that such joint can be represented as two revolute joints or something like that. Complex joints can always be represented by simpler models. Okay, so this is what can be done if that question comes to your mind. Like in case we have complex joints, not revolute and prismatic, then how many DH parameters will be there? So in such case, we say that okay, there are two revolute joints over there, and the distance between them is 0, something like that. Okay, so let's I will not go into, so this was the intuition and I will not go into like complete this thing, but these are the rules for drawing the axis and the finding out the DS parameters. We will come to them during the solving the questions. Okay, so let's do the, okay, someone wants to join. Okay. Okay, so in a welding industrial robotic manipulator, which section of the robotic manipulator is attached with the welding torch? So what is the answer? Anyone? Very simple, the simplest question that we are
End
going to discuss.
effector.
Yeah,
End
obviously,
effector.
the end effector. Uh, if you are attaching it somewhere else, then there is no point in having the robotic arm continue forward from that point, right? So this is the end effector, obviously. Uh, okay, so dash body arm configuration of a robot has the least complex kinematic modeling. So okay, so it is kind of a funny question because they are saying least complex kinematic modeling. So what is complex and what is complex kinematic modeling, that we do not know. but by intuition we can say that okay, there are different kind of arms over here. Okay, and okay, so let's look at each one of them. So what happens is, so this is the Cartesian coordinate body arm. So this is like a 3D printer. I hope everyone has seen a 3D printer or a GAN. It is also called as gantry robot. Okay, so it has only three prismatic joints. Okay, so one let's say about the z-axis, and then x-axis, and then about the y-axis. So it moves up, left, so you can reach any x, y, z position, right? So this is kind of the simplest arm that you can see, but once if you know the kinematic modeling, if you understand forward kinematics and DH parameters, then okay, I think all of them are easy. Okay, nothing is complex. But okay, for the sake of the question, we can say that okay, this is the easiest because uh, one argument can be these are all just prismatic joints, and only in z-axis we'll have for each joint we'll have motion about the z-axis, and it's much easier to find, less confusing. And let's assume angles are confusing, but I promise the angles are also not confusing. Okay, so let's move on to the next question. Select the kinematic parameter which is not fixed for a prismatic joint of a robotic arm. Okay, so anyone wants to answer this?
It will be link length and joint distance.
So only one answer is correct. Is the okay? Only one answer
Okay.
is correct. Okay,
So joint distance probably.
joint distance. Okay, so here the terminology is kind of weird. Okay, let me just figure out. Yeah, so answer is joint distance. Okay, usually in robotic literature we will have something called a joint offset and link length. Okay, or we can say that joint yeah, and link length kind of thing. Yeah, so I will give you the intuition about all the individual DS parameters, but the easy questions, let us just wrap up. Okay, choose the false statement. The Skara robot. Okay, yeah. So this we should be able to answer. Choose the Skara robot which has a wrist with rolling capacity. So what is a Skara robot? The Skara robot is something like this. Okay, so there is a z-axis here. Let's say there is a z-axis here, and then there is a motion along here. Okay, so and what they are saying, it has a rolling capacity. So at the end there is some rotational joint given. So after RP there is one more R. That's it. Okay, and so what is the number of degrees of freedom? There are 4 degrees of freedom, obviously, because there are 4 joints, right? And each of the degree of freedom will have 4 ds parameters, right? So it is like 4 into 4, 16. So we have, yeah, so this should be the answer. So a lot of questions are quite easy. Okay, so how many joint variables are there in forward kinematics of a spherical robot without considering the wrist assembly? Okay, so what do we consider as spherical robot can mean different to different people, but for the purpose here, we need to, let's say, this is the spherical robot. Okay, so you have you imagine like this. Okay, so there is a sphere. So what is a spherical robot? The spherical robot is kind of having the workspace of a sphere. Okay, so this is one joint. Okay, and so this is a, let's say, an equator of the sphere. Okay, so you should be able to point at any location on this sphere. Okay, and to point that we need only two angles. Okay, one you need latitude and one you need longitude. Okay, so one revolute joint will ensure that your latitude changes, and then there will be another revolute joint. This kind of a gun. If you have seen a tank, right, a tank, there is this tank, military tank, right? On the military tank there is a turret, and the turret has this pipe, right? Or the turret is the pipe. Okay. So so yeah, I think the turret is called pipe. So apologies for my lack of terminology knowledge. But so this is the top portion, and there is this. So if you see, this can also move like this, and this particular thing inside which the driver sits, the soldier who knows to drive the tank sits, also this also rotate. Okay, so this is kind of a spherical robot. Okay, the only difference here is that we have also put a prismatic joint at the end, so the radius of the end effector also along the sphere also can reduce. Okay, is everyone can imagine this? I think I have given good enough example in terms of this tank turret, huh? So you understand, like, the workspace of it. So it can, this will trace a sphere, right? This end effector will trace a sphere. Hello, anyone? Is everyone there, or am I audible? Am I audible? Just tell me if I am audible. You don't have to answer. Am I audible?
Yes, clearly audible.
Yeah, thank you. Thank you so much. Okay, I assume if you don't give the answer is yes. Okay, so yeah, so you can move on the surface of this imaginary sphere by these two revolute joints. Okay, and if you put an prismatic joint at the end of this turret, then you can also move inside and outside of the sphere. Okay, so it's kind of, you point and you can go up and down. So that is a spherical robot. Okay, so if so this is what I was trying to draw over here. And then in that case, what we say, that we have two joint variables that are angles and one joint variable that is distance. Okay, okay, so before we go on to these questions, we will now define the ds parameters and the rules for calculating the ds parameters. Okay, okay, so we know that there are 4 ds parameters: a, d, alpha and theta. Okay, so the d we say as the link length, a we say as the link offset, okay, we can, I think, let me just check distance along xi. Yeah, so this is the link length, this is the link offset, this is the twist angle, and this is the joint angle. Okay, now why the such names are given, the twist and all, is because let's say I have this kind of shape or some kind of link. Okay, okay, so z axis is in this plane and z axis is in this z-axis is out of this plane. Okay, so there is some angle between the two joint axes, and if I find that angle, then that is nothing but the alpha. If this link was not twisted, right, then the alpha wouldn't be there, right? So that is why it's called twist angle. uh, Joint angle, why theta is the joint angle, the angle about alpha, is because that we put the, that is, it is because the link is rotating in about z axis, right? So the link is rotating about theta, so we call it as joint angle directly. Okay, and in case of uh, prismatic joint, what happens is, along the z axis, if there is motion, like along the z axis there is motion, so that motion is d. Okay, so here if you see, d is the motion along z axis. Okay, so it is, so it is, d is the link, is the variable length. Okay, link variable. And if you see a, okay, now let's see how a, so let's say you have a finger. Okay, now when it is a perfectly fine finger, so sometimes what happens, we meet with an accident and this finger moves out of the plane, right? So this distance, kind of gross example, but that is what comes to my mind right now. This is a. Okay, so it is the how much the link gets offset from the earlier link. Okay, alpha is what, how much the link gets twisted. Okay, and a is how much offset is there. So you might have seen in robotic arms also, there is some offset that is there lot of times. So there is this, so one link is in this plane, then another link is over here, then there is again a motor, then again one more link is there. So there are like slightly different plane, the links are in slightly different plane, and it has to be because, imagine if they were all in the same plane, then the links will collide with each other, right? So having an offset is also sometimes beneficial. So in case of SCARA, right, if the links were in the same plane, both the links, this would have rotated and hit this link, right? This link would have rotated and hit this link. Okay, so we don't want that. So what we will do, we will have some kind of, offset. We put it in the another plane. Okay, now this link can rotate 360 without hitting this link. Okay, I hope you can imagine. Okay, so this is the meaning of the variables. Now let's define everything rigorously. Okay, uh, so whenever we are, if you want to write this down, please write this down. Okay, so these are the steps. If you follow these 9 steps, then you cannot get a wrong answer. Okay, so first we have to locate and label the joint axis. Okay, so let's have an example over here. Okay, so let me take a very simple example, and okay, so I have, okay, the simplest example can be a 2-hour manipulator, right? Okay, okay, so there are two joints, so this is 2-hour planar manipulator. Okay, so what is the first step? The first step is locate and label the z-axis. Okay, so this is joint 1 and we label the z-axis. So I will have a different color for each axis. So let's say z0, z1. If there was a prismatic joint, we would have put z2 on the axis of the prismatic joint. Okay, So we just have to blindly rotate and label all the z-axis. Now what we do, second step is we go for the x-axis. So for the x-axis, uh, okay, let's go in the order. Okay, once you get lot of practice, then you can do lot of things. But let's do the in the order. Okay, I'll just bring this slide in front of us so that we don't have to do back and forth. Okay. Okay. Yeah. So first step is what? Find the joints and put your z-axis. Okay. Second step is, so you can put the origin on the z-axis anywhere. So I put here. Okay. And then what you have to do is find the common normal between the z1 and z0. Okay, the consecutive z-axis, and put your origin over there. So what is the common normal between these two? It will be the line joining this. Okay, so I will put the origin here O1. Okay, and here, so we can always have a O0, O1, and 1 we can put on the end effector. Okay, O2. Okay, now the thing is, we have to establish this xi between the common normal of zi minus 1 and zi. Okay, so what is zi minus 1? So 0, O0 and O1. Okay, so we have to do is zi minus 1 and zi through OI. Okay, so for the uh, so what is the common normal between z1 and z0 through O1? Okay, so this particular example is very simple. We could have gone very fast, but still let's read the rules and follow the rules. Okay, so I put here. Okay, so this is my x0, and after that, similarly, at the end effector frame, okay, I can, okay, where is my marker? Okay, I can have z2 parallel to, so the end effector frame is always parallel to the previous frame, that you can remember. And then I can have z2 and z1 ka common normal, that is here, passing through the O2, right? And we have this as x1. And where will be the y? Y will be the by the right hand rule. Okay, so between x0 and z0, we have to have the right hand rule. So right hand rule will be saying this side. So when we rotate x0 to xy0, we get the z0. Okay. So this is the simple. And for the end effector frame, what we do? We just copy the frame just previous to it. Okay. So this is the uh, labeling of the axis. Okay. Now we need to find the ds parameters. Okay. So in order to find the ds parameters, what is the definition of the ds parameters, that we will see. Okay, so let's go over here, and this is the definition of ds parameter. So ai is along xi from oi to the intersection of xi and zi minus 1. Okay, so let's go step by step, understand what it means. Okay, I'll bring it here. Okay, once you practice lot of examples, then this will become very easy. So what is saying, distance along xi, okay, from oi to the intersection of xi and zi minus 1. Okay, so this is distance along xi, so this is right a1 a2, right, and so a is always in the direction of x. Okay, along the direction of d you have 0 distance, so our d1 and d2 is 0, right. So what is a1 and a2? This will be the link lengths l1 and l2. Okay, what is theta? Theta is the angle between x-axis, the two x-axis. What is the angle between x-axis? So let's say there is this origin frame. Okay, original frame, this x0 y0 z0 is there, but then there is a base frame. Okay, so with respect to base frame, this will rotate, but now it is aligned, so the angle is 0, theta is 0, but the when it rotates, the angle will become theta, so it will be theta 1 will be theta, right, and what will be theta 2 will be again the theta 2. Okay, what is alpha? There is no twist in this link, so there is no relative angle between the z axis, so alpha is 0, and here also alpha 1 is 0 and alpha 2 is also 0, because there is no twist between z2 and z1 also. Okay, so this is like sorry, no twist between z1 and the z0 and z0 and the base frame. Okay, so this is very simple, so I will just write our result in what we call as the ds table. So let's make a ds table over here. Okay, let's make it in the next slide. One, two joints are there. Okay, so this is, let's say, a, d, theta and alpha. Okay, so what is a? L1, L2, right? D is 0, 0. What is theta? Theta is theta 1, theta 2, alpha is 0, 0. Right? Anyone has doubt in this? This is the simplest example. Hello?
No, sir, it's clear.
It's clear, right? Anyone else? Like, okay, so it's just like you follow these rules. Okay, so I have put it in the slide. So these are taken from the book Spong and Vidyasagar. Okay. So this is the book. You can see it's a very short book, quick read, quite approachable. Okay, so I would recommend this book to you. Okay, so let's move on to this question. Okay, so they have labeled the axis for us. Okay, so we just have to use the definitions of the ds parameters. Okay, so uh, let's check their labeling. Okay, it would be interesting to check their labeling. So z0 they have put along the joint, fine. Z1 they have put along the joint, fine. Z2 also they have put along the joint. Now let's see whether x-axis is according to the label. So don't always expect that they will label the axis and give you. Okay, uh, you might have to, if they just give the manipulator, then we have to label the axis. Okay, and for that we have to follow the rules. So let me again bring the rules here. Okay, and just try to verify whether the labeling is according to our rules or not. Okay, so Z0 is along the joint, fine, and X0 and Y0 axis can be chosen conveniently to form a right hand frame. Okay, so there is no problem with this. Okay, now locate origin OI where the common normal to Zi and Zi minus 1 intersects Zi. Okay, so common normal to Zi and Zi minus 1. Okay, intersects Zi. So where does it intersect Zi? It will intersect here, right? No, Zi, right? So it will intersect here. So there we put what? There we put OI. So let me say I is equal to 1. The I under discussion is 1. Okay. So please pick up guys if I am becoming ambiguous or something like that. Okay. So Z1 is this, Z0 is this. So when we are saying common normal to Zi and Zi minus 1. So Z1 and Z0. Zi minus 1 is Z0. Right? Because I am only am not seeing your faces or something like that. So it's bit hard to get feedback in terms of in online sessions. So if you have some doubt, then please let me know. So Zi and Zi minus 1. I is equal to 1 currently. So Z1 and Z0. Okay. Now what is the common normal? Where does the common normal intersect? Okay. These two points right here. Okay. There can be more common normals also. No problem. Okay, but what we are saying is, we are saying locate origin OI. What is I? 1. So we are locating origin O1. Where are we locating? Where Zi minus 1, Z0 intersects Z1. Where it intersects? Here. So we are locating O1 over here. Fine? Right? Then what we say is, establish Xi along the common normal between Zi minus 1 and Zi. Okay, so we have to establish x1 along this common normal. So that is why they have pointed x1 along this line. So this is also correct. No problem.
I had a
Okay.
question.
Yeah.
I had a question. So
Yes.
when you say common normal, are we
Yeah.
referring to the main joint which is connected to the base of this robot? So that is always the common normal for any kind of serial manipulator
No,
that.
we are saying common normal in completely, see, it's geometric perspective. So common normal between Z0 and Z1. That's it. So Z0 and Z1, this is Z0, this is Z1.
Mhm.
This is the common
Yes.
normal, right? So this is the common
Okay.
normal. So this Z1 is going into the screen. Z0 is also going into the screen. So this normal is on the screen. Okay. So two parallel lines, the common normal will look something like this. There are infinite number of common normals, but for convenience we are putting it on the link itself, right? So this is O1 and then X1 will be along the common normal. Now what we say is uh, to choose y. So we have x and z. So we have to choose y such that this becomes a right angle triad. So, okay, so right hand rule follow, it should follow. So x is up, z is into the plane, so this will be like this. Okay, so y will be like this. So feel free to use your hands during the exam. Okay, uh, no problem. So this is y. So all three are correct. Okay, now let's move on to I equal to 2. What will happen if I equal to 2? Common normal between z2 and z1. Z2 we already had. How did we get z2? We just put z's along the joints. You don't think. Okay, you see if it's a prismatic or is a revolute, just put it along the joint. Okay. Now along the joint you can put inside or outside. Someone would put like this, no problem. Okay, so DS parameters are not unique. DS parameter just work. Okay, so that is why if you observe they are giving the axis, so that the answer, whatever answer comes should match. If they wouldn't have given the axis, then you would have taken any other any axis. Like let's say here x0 y0, you have freedom to choose, right? So if you see here x0 y0, choose conveniently. So you might get another values of ds parameters, they are also right. Okay, but then you cannot match the answer, so that is why they are preferring to give the axis over here. Okay, otherwise you should be able to label the axis. Okay, the axis should be labeled according to these rules. Okay, so that we are checking what are the rules. So these are the z2. Okay, now what is the common normal? Common normal between z1 and z2 is this, so that is why x2 is along it. And o3 will be where where will be o3? So sorry, o2, where will be the o2? So o2 where the common normal to z2 and z1 intersects z2. So the common normal to z2 and z1 intersects z2 over here. So this will be o2, origin of the second, this particular frame. Okay, clear? And then we put the end effector frame. Okay, so now we have x2 along the common normal, and we complete the right hand rule. We choose y such that right hand rule is getting completed, so y2 will be here, right? So it is also correct. Okay, and now we just copy this frame here to get the end effector frame. So this is z3, y3 and x3. Okay, fine. So this is the how we label it. Now let us find the what we call as the ds parameters. Okay, so this is very easy, you just don't get confused. Okay, just I have put the screenshots and you can practice. And I also give you some source of examples where lot of solved examples are there. Okay, so which follow exactly this convention. Okay, so there's this is a very good resource, Angela Soldman. There's a YouTube channel, and there are a lot of videos on ds parameter examples. Okay, so you can have practice from there, and so that you can check your answers. Okay, and also we'll go through each and one every step of like this, the way I am going. Okay, now let's find alpha, theta, a and d. Let's make the table. Okay, and that table only is the answer over here. Okay, so let's do that. So there is this a, d, theta and alpha. Okay, how many joints are there? 3 joints are there, so 3 rows will be there. Okay, so this is I equal to 1, I equal to 2, sorry, yeah, I equal to 3. Okay, so can anyone tell me the value of a? What should be the value of a? I'll put the what is the definition of a in front of you. Okay, and then you tell me the value of A. Okay, yeah. So A is the distance along xi from OI to the intersection of xi and zi minus 1. So just read it, take your time, take 1 minute, read this carefully, understand the meaning of it, and tell me the value of A1 when I is equal to 1. So that thing is readable, na? Or is it too small?
Yes, it's readable.
Uh, yeah, tell me.
So will it be 60 centimeters?
Where is 60 in this question? So there is only 140, I guess.
Okay, I assumed it was the difference between 100 minus 40, so that the distance is ending at
No, no, no. Just follow
this
this thing. Distance along xi. What is I1? Distance along
Mhm.
x1. Where is x1?
On the top. Yes.
Yeah, on the top. From O1. From O1 to the
Okay, to the yeah.
intersection of x1 and z0. Where is the intersection? So this is one point.
Mm-hmm.
O1 to the intersection of x1 and z0. This is z0.
100
Where, so this
centimeters.
is here. Yeah. So it is 100. Simple. So this is 100.
Got it.
Okay. So now, okay, where did this come? Okay, I'll put it here for now. Okay. Now tell me what is D1. Read that and tell me.
But sir,
Sir, it
no.
is bit blurry. Kindly just
Okay, I
increase a
will.
bit.
Yeah, I will increase. Okay. Thank you for telling. Okay, let me. Okay. So what can I do is now. Can it? Is it visible?
Yes, sir, better.
Okay. So distance along zi minus 1. So I want d1. So it will be distance along z0. Someone is joining. Okay. No. Here. Okay. So let me just check the recording. Yeah, it's recording. Okay. So distance along z0. So this particular axis z0 from O0 to the intersection of x0, right? So this is one point is O0. Okay. To the intersection of what? It x1 because I is 1 and zi minus 1 z0. So it is here only. So the second point is also here only. So what will be d? 0. Because these 2 points, so distance you are getting distance along z0 from o0 to the intersection of xi and zi minus 1. Intersection of x1 and z0 is also z0 only. Okay, so that is why both the points are same, so di will be 0. And intuitively, if you think, there is no offset, right, between these two. The example of offset you remember, right? So the links are not out of plane. They are in the same plane. When we say out of plane, it is like along the z direction they should be out. So if there is this joint, right, there is this joint, the angle is moving, it should be above here and it should move. That is not happening. So it makes sense also D. If you follow here, this is also fine. Or intuitively also you can check your answer is right. So D is 0. What is theta?
It'll be
The
90 degree because there is a 90-degree angle between the intersecting points.
So the angle between xi minus 1, that is x0 and x1, okay, measured about z0. So this is z0 over here, okay, and we have to find angle between x1 and x0 about z0. So what is that angle? It is just theta, right? So when this rotates, when x1 will rotate, it will be theta only, right? So what is alpha? Angle between zi minus 1 and zi. So angle between zi minus 1, z0 and z1, right? So what is the angle between them? 0 about xi, but they obviously they are parallel. So 0, there is no twist. Okay, there is no twist. So this is 0. Okay. Now let us move on to the I equal to 2. Okay. So for I equal to 2, again let we follow the same thing. Now I will try to go faster. Okay, so that you understand that okay, it's really not that complex as we think it looks to be. So when I equal to 2, distance along x2 from O2, so O2 is here. Okay, distance along x2 means along this line. Okay, to the intersection of x2 and z1. So x2 and z1 intersect over here. Okay, so what is the distance between these two? Is 40. Fine, so we can just write 40. Okay, d, what is d? D should be what? The distance along z1 from O1. So distance along z1 from O1 to the intersection of z2, sorry, x2 and z1. Okay, so what is that intersection? Again, this point only, x2 and z1. See, intersection of, where is z z1 and x2. Where do they intersect? It intersects here only, z1 and x2. And the earlier point is also this one, O1 only. Okay, see this. I equal to 2 is going on, so this is what? O1. So again, both the points are here only. So there is no distance between that. So again, D will be 0. Okay. Again, so x2 is over here and x1 is over here. So what is theta? Angle between xi minus 1 and xi measured about zi minus 1. So the angle between xi minus 1, that is x1 and x2 measured about z1. So z1 is inside the plane. So here you please pay attention, okay, and ask me again. So z1 is inside the plane, x2 is here, x1 is here. Okay, so this is the angle between what? x1 and x2. So what is the angle between x1 and x2? If z1 is inside, so x1 has to be rotated by 90 degrees, right? To reach x2. So about z axis, if you put the right hand rule, so x1 has to rotate it by 90 degrees. Okay, so this is plus 90 plus theta, and but because it is a joint, so it will be 90 plus theta. Okay, what is alpha? So this is very important, 90 plus theta. Okay, they haven't asked the theta values in the question. Okay, this is theta 1 and theta 2. But this is important that you write 90 plus theta, not just theta 2. Otherwise, when you are doing the simulation or anything, you will not get the right answer. Okay, just follow this rule, you will automatically get. So there is a 90-degree offset by labeling the axis, and then there is the joint angle, not directly. Already x1 and x2 are at 90 degrees. Okay, here what happened, x0 and x1 were aligned, and then the rotation of the joint was causing theta. So it was theta plus 0, theta 1 plus 0. Here it is 90 plus theta. So initial position 90-degree offset, and then whatever the link rotates. Okay, so again, what is alpha 2? Alpha 2 is the angle between Z2 and Z1, right? Measured about x2. So this is x2, angle between Z2 and Z1 is 0 because they are parallel. So alpha is again 0, which we can see the link is not twisted. Okay, so for the last part, okay, so O3, what is the, what is this? You can feel it here. So I will intuitively feel alpha is 0, theta will be theta 3 because the x-axis are in the same direction, and d will be 0 because there is no offset, and a is the link length in that direction. So have they given? They haven't given, but if they had given some this distance over here, it would have come over here. Okay, so you can fill in the answers over here. But we have found more than the answer. Okay, and we have also seen that verified the labeling process. Okay, fine. Anyone has doubts? It's pretty simple, right? It's just, following the rules. Okay, so we'll we'll also give you a link in chat if you want to practice more. So is this wonderful, if you search this, okay, you will get lot of examples over here. Okay, something like this. So I will just give you a
The
link of that,
shortcut method.
link of that also. Okay, but just follow this screenshot that I had shown you. Okay, it's all over the place. Okay, fine. So here is the chat window, and this, yeah, there's a lot of more educational stuff also available on this channel. So see, this is the thing, when you are doing the course, try to see also the application, and that we will see now. Okay, what is the application of all this? Okay, so how exactly by finding DS parameters are we doing forward kinematics? That is the question. So we started by saying that, okay, this is the forward kinematics lecture, and where is the forward kinematics? Okay, so the thing is here. Okay, let me just clear this. Okay, garbage, put it over here. Okay, so we had seen in previous lecture, I had given you a shortcut formula, that was this. Between two frames, if you have given the ds parameters theta, d, a and alpha, how to find the homogeneous matrix between the two frames, right? Now you see that if you have the ds parameters, parameter table, okay, so and you have this a, d, alpha and theta for all I equal to 1, 2 until the n links. What happens is you have all this a, d, alpha. So you have a1, a2, a3 till, let's say, an, where a1 is the homogeneous matrix between the first two frames, then a2, a3, so on. So what you just have to do is you have to multiply all these matrices and you get the homogeneous transform for the entire. Okay, someone is joining. Yeah. So you get the homogeneous matrix for the entire manipulator. Okay, entire manipulator. Okay, so it will be 4 cross 4 matrices multiplied, and it will be like A is equal to, okay, A1 into A2 into A3 to like that AN. So you multiply this and then you will get the homogeneous transform. And what is homogeneous for transform? How is it related to the forward kinematics? If you see these 3 entries of the homogeneous transformation matrix that will come up, okay, so this will be 0 0 0 1 and 0, where there will be some 3 entries. What will be that? That will nothing be the position of end effector, right? That will be the position of end effector in terms of what? As a function of all this A, D, alpha, theta for all the links. So this is the forward kinematics. Okay, so this is how you get the forward kinematics. Now if you have any doubt, please let me know. Then we can do some example in MATLAB and see how to use this forward kinematics for a 2-hour manipulator. Okay, do you have any doubt? So this what you see here is just how to calculate A1 for A2. Okay, for
I have
just
a
one.
question.
Yeah, yeah.
I'm sorry.
Hmm.
Is this multiplication that you're showing us, this
Hmm.
is similar to what we studied in the previous class for showing translation of fixed and mobile frame?
Not just translation, no. So it's like transformation. It's not
Okay.
just
So,
translation. Yeah, it is like
right.
rotation plus
So,
translation. Yeah.
yes, rotation plus translation. So, there was another additional matrix that you had shown us that as a quick method, instead of multiplying each and every matrices individually. So, which
Ah,
one is
yeah,
that?
yeah.
Is that the one?
So this is when DS parameter is given. Once we have found out the
Okay.
DS parameter, see what happens is a robotic company will have to give specifications of its robot, right? So it will not give you the matrices. It will just give you the DS parameters, the table. From the table, you know what is the link length, or what is the offset, what is the twist in the links, right? So you know what is the workspace of the robot. Okay, by just
Yes.
multiplying these
Yes.
matrices. Okay, that method is when you have been given the 2 frames. Okay, 2 frames, and you have to find the homogeneous matrix between these 2 frames only, and the 2 frames are mentioned by the unit vectors f1, f2, f3, m1, m2, m3. Okay, you have been given the unit vectors between the two frames. Like for example, there is this global frame over here, global frame, and someone tells you that okay, f1 is some 1 I cap plus 2 j cap plus 3 k cap divided by the mod of this vector. So you get a unit vector. Then f2 is perpendicular to it and something like that. So you only know the vectors, unit vectors. In that case, you do this dot product formula, which was something like f1 dot m1, f2 dot m2, f3 dot m3, and let's say f1 dot m2, f1 dot m3 and all. So that was the shortcut formula. Okay, this formula I showed you in the last question, where you were given the DS parameters and you had to find the homogeneous matrix between 2 frames. So this is just homogeneous matrix between just 2 frames. Now there are n links, so there are n frames. So you just multiply all this in the order. Okay, so let me just check the order. Am I making some mistake over here? Oh yeah, yeah, I'm making a mistake. So the order is like this: is an equal to a1 into a2 into a3 into dot dot dot, like that, an. So this is the transformation from t0 to nth frame. Okay, you multiply them in order, so you will get the homogeneous matrix from the base frame to the end effector directly. Okay. Does that answer your question?
Yes, I got it. So the main thing is to follow the DH table. That would be clear.
Yeah, follow the DS table and find the individual A1, A2, A3 by
Hmm.
this
Okay.
matrix. Okay, yes, theta, I don't know if it's too small. Okay, so here you have this. My God, so
Okay.
I have still not figured out how to, use this pen and stuff. Okay, but yeah, I will put it over here. Okay, so you can see this matrix is function of alpha, theta, and all. So
Yes. Yes.
yeah. So you will get for every link, sorry, every joint, every two joints, you'll get one this matrix, and then you can multiply all of them. Okay, then you will get and the forward kinematics will be these three entries of the matrix of the complete matrix after multiplication. So we will try to do that in MATLAB. Okay. Okay, so let's go to the MATLAB. I assume everything is clear. If it's not clear, there is one more TA session coming up on Tuesday. Uh, you can attend that, or you can ask me in the next one. Okay, so uh, let's do it for. So this is okay. Everyone is able to see the MATLAB screen.
Yes. Yes.
Yes.
Yes, sir.
Uh, is there anyone who doesn't know MATLAB at all? Like so that I want to go from the basics, like because there is nothing like you will learn the entire MATLAB now. Okay. Okay, so I think everyone, nobody is answering. That means you have some idea. Okay. Okay, so let's do this. So this is called the editor window, and in the editor window, uh, last time we were doing some executions in the command window. So but then you do line by line, right? In editor window you can write lot of code
Sir,
together
please
without.
go from the basics because I have just joined today. It would be
Okay,
helpful
okay,
if you go from the basics.
okay, we'll do that. Okay, so uh, okay, so this particular portion of the MATLAB is called command window, and this portion is called the editor window. So in command window, what we do is we can just write a command, let's say d equal to 1, and we can see what is the output. Okay, or if you want to write the matrix, then what we do is we have a square bracket. Okay, and we write the first row. Okay, and the elements of the row are written by giving space between them, and element while writing the element of next row, we put the colon. Okay, semicolon. Okay, and then we write the, let's say this, and if you press enter, you see the D matrix is coming. Okay, fine, and the variables you can see over here, this is called the workspace. Okay, so now for the 2R manipulator, okay, we had found the DS parameter, right? So before that, let's define the link lengths of the manipulator. Let's say both the link lengths are 1, L1 and L2 is equal to 1. Okay, then we know that alpha 1 is equal to 0 and alpha 2 is equal to 0. We have found this. We know that d1 equal to 0 and d2 equal to 0. This also we found, right? So you might notice that after every line I'm putting a semicolon. That is because if I don't put a semicolon, you will get the output when I run the code. So let me show you what happens. Let's say I don't put the semicolon for this particular line. When I run the code, to run the code, you can go to this green button over here, and yeah, I have to save the code somewhere. So let's call it 2 degree of freedom manipulator or something like that, random name, and I save over here. Okay, so we cannot start the name of the file by a number, so let's call it a planar 2dof. Okay, okay, I change the folder. Okay, we are here. Okay, so now I run this. So you see I get alpha 1 equal to 0, alpha 2 equal to 0. It's getting printed. I don't want it to get printed unnecessarily, so I just run like this, and you see now nothing got printed. Okay. If I want to clear this particular screen, then I will just write CLC at the start. So first thing it does is it clears this window, and so everything is clean. Okay. And if I want to clear the workspace, then I can use the command clear. Okay. So yeah, so it cleared the workspace and then it executed this command. So now the only variables that are related to our code. Okay, so we defined this, and then theta, let's have give some values of theta, because this is the idea of forward kinematics, right? So the idea of forward kinematics is that we know theta and we want to find the end effector position. So let's give some thetas that we can verify. So let's give theta 1 is equal to 0 and theta 2 equal to 0. So we know that when theta 1 and theta 2 equal to 0, our manipulator will look like a straight line because both the links will be parallel, right? Yeah. So let's now find the end effector positions. Okay. So how do we find the end effector positions? So the if I do the geometric way, it is very simple. I can just write this L1. Okay, I will just show you here. Okay, so let's do it here. Okay, so this is some other slide. Which the slide we were working? Yeah, yeah, yeah. So here some spaces there. Okay, so if I have two links and this is theta 1, okay, and this is theta 2, and I want to find the coordinate over here, I can do this geometrically also, right? So by this is L1 and this is L2. So this particular point is what? L1 cos theta 1, and so till here distance is for x-axis, x1 will be, if I want to find xe, ye, so this will be xe will be L1 cos theta 1 plus L2 cos theta 2, right? If I measure all the angles with the x-axis, right? But in case of DH, what we are doing, we are measuring angle with respect to the current axis. So this is theta 2, so this will be theta 1, this will be theta 1 geometrically, and this will be theta 1 plus theta 2, and similarly ye will be L1. So you can verify this later. Okay, this is sine theta 2 plus theta 1 plus L2 sine theta 1 plus theta 2. Okay, so this is just by geometry, but and it is very simple. It's just two lines of code, but we want to see how to do it by ds parameter. So what we'll do is we'll write the transformation matrix A1. Okay, so we have all these parameters alpha 1, L1, D1, right, theta 1. So let's find the transformation matrix A1. What is A1? So A1, according to the formula that we just discussed, right, was what? Cos theta 1. So I will just pull up this from my earlier code, okay, for to save the time. So but I am doing it in front of you so that you understand that how easy it is to do this. So this is A1, okay, and I will just change all the variable names to theta 1, alpha 1, like that. At any point of time, if you have any doubt, please you stop me, because that is the purpose of the session. Okay, and since I am not able to see you also, so it's in your interest to ask doubts.
So kindly explain the this matrix means after After
Okay.
what you have written.
Yeah. Yeah. So this matrix that we discussed, this is the same matrix. Okay. So here that we saw, na, where did we see that? Yeah. This matrix. We discussed this matrix, right? This matrix we get after from the DS parameters. This is the transformation between two frames, right? Related by this alpha, theta, D and A. Okay. So this matrix only, if you see MATLAB, this cos theta I, right? So for I is equal to 1, this is cos theta 1. I have written D because I am giving angle in degrees. If I give in radian, I will write cos only. To test, I will just show you over here. See, if I do cos of pi, I get minus 1. If I do cos d of 180, because I am doing 180, I have to write d, I get minus 1. Okay, it's just to substitute in this thing. So yeah, so the point is that this is that matrix that we just discussed. Okay, fine. And how do we write this matrix? If that is your question, then we, for the first row, in the row, we put only space between two entries. Okay, and then colon. So if you see this matrix, cos theta minus sin theta cos alpha, right? So between these two entries, I have a space. If you see here in the code, I have a space. I am highlighting it with blue. Okay, and before starting the next row, I put the colon. Okay, so this is how you define the matrix. If you want to see how it looks, yeah, then I can just remove this semicolon and run. Okay, the output is here and there is some error and it says that unrecognized variable a1. Okay, that is because we forgot to define a1. So a1 is what? L1, and a2 is what? L2. As you can see, from the derivation, we had found that a1 and a2 is L1, L2. Okay, now if I run, I'll get the matrix. So this is the matrix we are getting. Okay, and let's try to understand whether it is correct. So for just one link, this is the transformation for just one link, right? And you see where is the end point of the link? Here, these three values. I hope you can see my cursor, and that is 1 0 0, which makes sense, right? So it is just moved one direction in the x-axis, that is along the link length. X is along the link length, right? And then along z and y it is 0. So this point is correct. Okay, now let's find a2. Okay, to find a2, again we'll paste it over here and we'll just, instead of theta 1, we give theta 2. Don't worry, I will just revise entire procedure. For now you just focus on the code. I will revise the entire procedure for the 2R manipulator. Okay, and we'll also plot and see how it is looking. Okay, so that way you can also learn plotting. So we have 2 hours, but so we have to utilize them in some way productive and not just learn what is there in the course. Okay, so also apply why we are learning in the course, that also we have to learn. Okay, so this is the A2 matrix. Okay, now there is something. So this is the A2 is what? Transformation between the end effector and the second joint. A1 is what? Transformation between second joint and the first joint. Fine, there are only two joints. Okay, so now how do we find the transformation between the end effector and the origin of the manipulator, that is by, so we have A1 and A2 now. Okay, let me just draw the, okay, eraser. Okay, let me write what are the steps that we followed. Okay, first what we did was we draw the 2R manipulator, right? We drew the 2R manipulator. Then what we did, we labeled the axis according to DH rules. Okay, we label axis. Okay, then what we did, we found DH parameter table. How the table looked? The table looked like A, D, theta, alpha, L1, L2. D was 0, 0, theta 1, theta 2, and 0, 0. It looked like this. Okay, then what we did, from this we found A1. From A1 we found from the L1 0 theta 1 alpha 1, and A2 we found from L2 D2 theta 2 alpha 2. Now what we should do, just multiply A1 into A2, right? And that will get the relation between the zero the zeroth frame and the second frame. That relation we'll get, and from this relation we'll find the position of the end effector, and we'll see that. Okay, so now I just multiply A1 into A2, and notice that I am not putting semicolon. So if I don't put semicolon, that output will get printed in the command window. So I see, so now A1 into A2 is, answer is equal to this 200. Now you think, is 200 correct? So this was the x-axis, x1, right, x2, right? So if I put a fixed frame at the base, so this point will be 200 because link length is 1 and 1, right? Agreed, everyone? So we are getting correct endpoint from the link angles, angle 0, 0. Let's say we put angle 0 over here and angle 90 over here. So the end effector will look like this. What will be the coordinate of this point? 1 comma 1, right? Let's see whether we are getting that. Let's change the angle. Okay, let's do theta 2 is equal to 90. Okay, so it depends on what is our z axis, but let's see. Okay, but we are getting what? X1, Y1, right? That is what we were expecting. The coordinate of this point is 1 comma 1. If we rotate by minus 90 degree, what will happen? We need to check our answer. We'll get, if the rotation was about minus 90, so it would will look like this. So this direction is minus 1. So the coordinate is what? 1 comma minus 1, right? So this works, right? Whatever we did is working, and this is the forward kinematics, because why? We change the angles and we get the end effector position. If I want to pull out the end effector position and only print this much, then what we will do? We can just, we say that this entire matrix is equal to A, and we find the numbers in the third column, sorry, the fourth column, and all the values. Okay, or we can say first 3 values. Okay, I will explain this notation. Just for now, just see how it works. Okay, so what is the wrong over here? This is not column, this is first value is row. So okay, we want first 3 rows and the fourth column, right? So first 3 rows and the fourth column. So what we say, I want A of 1 to 3 row, this colon means 2, first row to the third row, comma, fourth column. Okay, and I run and I get the position. X is 1, Y is minus 1 and Z is 0 when the angles are theta equal to 0 and theta equal to minus 90. Fine. Okay, and let's say you want to visualize this. Okay, so as I had told that the application of forward kinematics is basically visualization. For control you will use inverse kinematics because you know where your forward for end effector should be placed. If you are doing welding, you know where the end effector should be. What you don't know is how the robot should move to do this, right? What should be the joint angle? So that is inverse kinematics. That we will see in the upcoming lecture how to do that. But let's say uh, uh, I want to plot this. So what we can do is I should have how many points to plot this? 3 points, the origin, the first joint and the third joint, and then I can draw lines in between them, right? So how do I do that? Okay, so let's have all the points. Okay, so let's have all the x coordinates. So the first one will be 0, right? Second one will first one will be, yeah, 0. Second will be the x coordinate of the A1 matrix, but which coordinate, which from A1 matrix we have to find that coordinate, and what is the x coordinate? It will be the fourth row, first row, fourth column. So first row, fourth column, right? This is the second point, and what is the third point? A matrix, right? End effector is in the A matrix, A1 into A2, and so that will be A of first row, fourth column. Okay, similarly, let's find the y's. Y will be in the what row? Hello, y will be in what row? Second row, right?
Second row. Yeah,
Yeah,
second
so
row.
instead of 1 I will do 2. Okay, since this is a planar manipulator, I don't really have to worry about z. So x0 and y0, I found x0, y0. Now I just say plot, right, x0 comma y0, or just let's name it x, y, because it's not some kind of, so let's name it xy. Okay, and see here, plot function, what it will do, first you have to give the x coordinate and then y coordinate, and then you give the color whatever you want or the style of the this thing. So I just give, let's say, O or something like that, or if I want it in blue color I will give blue or something. Then what we'll see what is the output. Okay, if I run this I get a plot. Okay, but you see I got 3 points over here, but it's not visible. Okay, so we have to define the limits of the axis. So we give x limit is equal to, so we are just limiting the size of our plot. So this is let's say minus 2 to 2, and y limit is equal to this. Okay, if I run this, I get 3 points. Okay, uh, okay, I have to write it y limit. Okay, so you can see I got 3 points, but they are not joined. Okay, so let's remove this. Okay, so I get this manipulator. Okay, I can change the line width and all, so that also you can do over here. So these things you don't have to remember, you can always Google how to change the line width, and then if you get the answer in the first try it's fine, otherwise you can, yeah. So this is how we get when theta 2 is equal to minus 90 and theta equal to 0, right? Let's change the theta and see. Let's change theta 1 to 30 degrees. Okay, so let's see if it moves by 30 degree. Yes, it moved by 30 degree, and the second angle is 90 minus 90 degree, right? So is it fine, everyone? So you can see the end effector.
Yes, sir.
Yeah, yeah. So now you understand that for, so if I can also do animation. Okay, if I want to do animation, I can do that. We still have 16 minutes to go. Do you want me to do it, or it's too much in one lecture?
Next day would be preferred.
Okay, we still have a lot of tutorials coming, and we can do that next time. But what my message is here is that whatever you are learning, it's pretty basic stuff. Okay, so it's not about just solving the questions. You just see how, just follow the procedure, and those things are useful. Okay, it may look that okay, it is lot of math is there, but it's not too much. When you're applying, you if you just follow the procedure, you can do some cool stuff with it. Okay, so as simple as just multiplying two matrices, it didn't took me like 20 minutes over here just to write this code, right? So I will try to share this code also. You can play with it. If you don't have MATLAB, it can work in Octave, that is open source. Okay, so if there is any other doubts, please ask. I can see only one person usually asking doubts. Others, please, you also speak up if you don't understand. Maybe next time we will try to ask about everyone, their background or something like that. We can have some more talks to understand what really you are expecting.
Sir, is there any chance, as I have joined only today, I have to cover all the lectures and submit the assignments.
Yeah,
So
yeah.
is it
So
possible that this,
see our all the TAs. So the lectures are available. You can watch the lecture. You have to watch the lecture. There is no other option. And a lot of lectures haven't like only 2 weeks lectures have happened, right? So it's not a big deal. You can watch before 9th. 9th is I think the deadline for assignment 1. So 1 week lectures are pretty basic. You can watch that. And after that,
it for assignment
for
1 and 2?
assignment, huh?
It is ninth is for assignment 1 and 2.
Yeah, yeah. For 1 and 2, then watch the both the lectures. You should have watched till now. This is just TA session. So this we are just helping you out with the assignment related some similar questions that can help you do your assignment on your own. Okay, so
Okay.
we have already uploaded to Daniel. We have already uploaded our videos on our YouTube channel. Okay, of the previous session, so you are not going to miss anything. Okay,
So
so you
YouTube
can,
channel, can you share the link?
yeah, I will share the link. So I will your channel. Yeah, so this is my channel, and this is that video, week 1 video. And you can also watch the videos of other TAs. I will also share their link if I can find that. Okay, I will also share the YouTube link of other TAs. So this is of Suman and Abhishek also I will share. Yeah. So you go to the, when you see that video, whatever channel is there now, you can, that is the YouTube channel. Okay, so this is for Daniel. If you have missed the session, week 1 session, you can watch it here. Is that fine? Hello?
Yes, it is fine.
Yeah, yeah. Okay, I think if there are no doubts, then we can end our session here and we'll meet next time and do some cool stuff if time permits. Okay, bye.